The real magic of the rainbow. When I was about 10, I was taken to London to see a children's play called Where the Rainbow Ends. You almost certainly won't have seen it because it is too unfashionably patriotic for modern theaters to perform. It is all about how exceptionally special it is to be English, and at the climax of the adventure, the children are rescued by St. George, the patron saint of England, not Britain, for Scotland, Wales, and Ireland have their own patron saints. But what I most vividly remember is not St. George, but the rainbow itself. The children actually went to the place where the rainbow planted its foot, and we saw them walking about in the middle of the rainbow where it hit the ground. It was cleverly staged, with colored spotlights beaming down through swirling mist, and the children stumbled about in a spellbound daze. I think it was at about this moment that the shining armored, silver-helmeted St. George appeared, and we children gasped at the scene as the children on the stage shouted, "St. George! St. George! St. George!" But it was the rainbow itself that seized my imagination. Never mind St. George. How wonderful it must be to stand right in the foot of a giant rainbow. You can see where the author of the play got the idea. A rainbow really does look like a proper object, hanging out there, perhaps a few miles away. It seems to have its left foot planted, say, in a wheat field, and its right foot, if you are lucky enough to see a complete rainbow, on a hilltop. You feel you ought to be able to go straight to it and stand right where the rainbow steps on the ground, like the children in the play. All the myths I have described to you have the same idea. The rainbow is seen as a definite thing in a definite place, a definite distance away. Well, you probably have worked out that it really isn't like that. First, if you try to approach the rainbow, no matter how fast you run, you'll never get there. The rainbow will run away from you until it fades away altogether. You can't catch it, but it isn't really running away because it isn't really in a particular place at all, ever. It's an illusion, but a fascinating illusion, and understanding it leads on to all sorts of interesting things, some of which we'll come to in the next chapter. What light is made of? First, we need to understand about something called the spectrum. It was discovered in the time of King Charles II, that's about 350 years ago, by Isaac Newton, who may well have been the greatest scientist ever. He discovered lots of other things besides the spectrum, as we saw in the chapter on night and day. Newton discovered that white light is really a mixture of all the different colors. To a scientist, that's what white means. How did Newton find this out? He set up an experiment. First, he blacked out his room so that no light could get in, and then he opened a narrow chink in the curtain so that a pencil-thin beam of white sunlight came in. He then let the beam of light pass through a prism, which is a sort of triangular chunk of glass. What a prism does is splay the narrow white beam out, but the splayed-out beam that emerges from the prism is no longer white. It is multicolored like a rainbow. And Newton gave a name to the rainbow he made, the spectrum. Here's how it works. When a beam of light travels through air and hits glass, it gets bent. The bending is called refraction. Refraction doesn't have to be caused by glass. Water does the trick too, and that will be important when we come back to the rainbow. It is refraction that makes an oar look bent when you stick it in the river. So, light is bent when it hits glass or water. But now, here's the point. The angle of the bend is slightly different depending on what color the light is. red light bends at a shallower angle than blue light. So if white light really is a mixture of colored lights, as Newton guessed, what's going to happen when you bend white light through a prism? The blue light is going to bend further than the red light, so they will be separated from each other when they emerge from the other side of the prism. And the yellow light and the green light will come out in between. The result is Newton's spectrum, all the colors of the rainbow arranged in the correct rainbow order: red, orange, yellow, green, blue, and violet. Newton wasn't the first person to make a rainbow with a prism. Other people had already got the same result, but many of them thought the prism somehow colored the white light, like adding a dye. Newton's idea was quite different. He thought that white light was a mixture of all the colors, and the prism was just separating them from each other. He was right, and he proved it with a pair of neat experiments. First, he took his prism as before and stuck a narrow slit in the way of the colored beams coming out of it, so that only one of them, say the red beam, passed through the slit. Then he put another prism in the path of this narrow beam of red light. The second prism bent the light as usual, but what came out of it was only red light. No extra colors were added, as they would have been if what prisms did was add color like a dye. The result Newton got was exactly what he expected, supporting his theory that white light is a mixture of light of all colors. The second experiment was more ingenious still, using 3 prisms. It was called Newton's experimentum crucis, which is Latin for critical experiment, or as we might say, experiment that really clinches the argument. On the left of the picture above, you see white light coming through a slit in Newton's curtain and passing through the first prism, which spreads it out into all the colors of the rainbow. The spread out rainbow colors then pass through a lens, which brings them all together before they pass through the second of Newton's prisms. This second prism had the effect of merging the rainbow colors back into white light again. That already neatly proved Newton's point. But just to make quite sure, he then passed the beam of white light through a third prism, which splayed the colors out into a rainbow again. As neat a demonstration as you could wish for, proving that white light is indeed a mixture of all the colors. How raindrops make rainbows. Prisms are all very well, but when you see a rainbow in the sky, there isn't a great big prism hanging up there. No, but there are millions of raindrops. So does each raindrop act as a tiny prism? It is a bit like that, but not quite. If you want to see a rainbow, you have to have the sun behind you when you look at a rainstorm. Each raindrop is more like a little ball than a prism, and light behaves differently when it hits a ball from how it behaves when it hits a prism. The difference is that the far side of a raindrop acts as a tiny mirror, and that is why you need the sun behind you if you want to see a rainbow. The light from the sun turns a somersault inside every raindrop and is reflected backwards and downwards where it hits your eyes. Here's how it works. You are standing with the sun behind and above you, looking at a distant shower of rain. The sunlight hits a single raindrop. Of course, it hits lots of other raindrops too, but wait, we're coming to that. Let's call our one particular raindrop A. The beam of white light hits A on its upper surface where it is bent, just as it was on the near surface of Newton's prism. And of course the red light bends less than the blue, so the spectrum is already sorting itself out. Now all the colored beams travel through the raindrop until they hit the far side. Instead of passing through into the air, they are reflected back towards the near side of the raindrop. this time the lower part of the near side. And as they pass through the near side of the raindrop, they are again bent. Again, the red light bends less than the blue. So, as the sunbeam leaves the raindrop, it has been splayed out into a proper little spectrum. The separated colored beams, having doubled back around the inside of the raindrop, are now hurtling back in the general direction of where you are standing. If your eye happens to be in the path of one of those beams, say the green one, you'll see pure green light. Somebody shorter than you might see the red beam coming from A, and somebody taller than you might see the blue beam from A. Nobody sees the full spectrum from any one raindrop. Each of you sees only one pure color, yet all of you say you see a rainbow with all the colors. How come? Well, so far, we have only been talking about one raindrop called A. There are millions of other raindrops, and they are all behaving in the same kind of way. While you are looking at A's red beam, there is another raindrop called B, which is lower than A. You don't see B's red beam because it hits you in the stomach, but B's blue beam is in exactly the right place to hit you in the eye. And there are other raindrops lower than A, but higher than B, whose red and blue beams miss your eye, but whose yellow or green beams hit your eye. So lots of raindrops together add up to a complete spectrum in a line up and down. But a line up and down is not a rainbow. Where does the rest of the rainbow come from? Don't forget that there are other raindrops stretching from one side of the rain shower to the other and at all heights. And of course they fill in the rest of the rainbow for you. Every rainbow you see, by the way, is trying to be a complete circle, with your eye at the center of it, like the complete circular rainbow you sometimes see when you water the garden with a hose and the sun shines through the spray. The only reason we don't usually see the whole circle is that the ground gets in the way. So that's why you see a rainbow at any one split second. But in the next split second, all the raindrops have fallen to a lower position. A has now fallen to where B was, so now you see A's blue beam instead of its green one. And you can't see any of B's beams, although the dog at your feet can. And a new raindrop, C, whose beams you couldn't see at all before, has now fallen into the place where A was, and you now see its red beam. That's why a rainbow seems to stay still, although the raindrops that make it are constantly falling through it. On the right wavelength? Let's now look at what the spectrum, the ordered range of colors from red through orange, yellow, green, and blue to violet really is. What is it about red light that makes it bend at a shallower angle than blue light? Light can be thought of as vibrations, waves. Just as sound is vibrations in the air, light consists of what are called electromagnetic vibrations. I won't try to explain what electromagnetic vibrations are because it takes too long, and I'm not sure that I entirely understand it myself. The point here is that although light is very different from sound, we can talk about high frequency, short wavelength, and low frequency, long wavelength vibrations in light, just as we can for sound. High-pitched sound, treble or soprano, means high frequency or short wavelength vibrations. Low frequency or long wavelength sounds are deep bass sounds. The equivalent for light is that red, long wavelength, is the bass, yellow the baritone, green the tenor, blue the alto, and violet, short wavelength, the treble. There are sounds that are too high-pitched for us to hear. They are called ultrasound. Bats can hear them and use the echoes for finding their way around. There are also sounds that are too low for us to hear. They are called infrasound. Elephants, whales, and some other animals use these deep rumbles for keeping in touch with each other. The deepest bass notes on a cathedral organ are almost too low to hear. You seem to feel them fluttering your whole body. The range of sounds that we humans can hear is a band of frequencies in the middle, between ultrasound, which is too high for us but not for bats to hear, and infrasound, which is too low for us but not elephants to hear. And the same is true of light. The color equivalent of ultrasound bat squeaks is ultraviolet, which means beyond violet. Although we can't see ultraviolet light, insects can. There are some flowers that have stripes or other patterns for luring insects in to pollinate them, patterns that can only be seen in the ultraviolet range of wavelengths. Insect eyes can see them, but we need instruments to translate the patterns into the visible part of the spectrum. The evening primrose flower on the right looks yellow to us with no pattern, no stripes. But if you photograph it in ultraviolet light, you suddenly see a starburst of stripes. The pattern in the lower picture is not really white, but ultraviolet. Since we can't see ultraviolet, we have to represent the pattern in some color that we can see, and the person who made the picture decided to use black and white. He could have chosen blue or any color. The spectrum goes into higher and higher frequencies, far beyond ultraviolet, far beyond what even insects can see. X-rays could be thought of as light of even higher pitch than ultraviolet, and gamma rays are even higher still. At the other end of the spectrum, insects can't see red, but we can. Beyond red is infrared, which we can't see, although we can feel it as heat, and some snakes are especially sensitive to it, using it to detect their prey. I suppose a bee might call red infraorange. Deeper bass notes than infrared are microwaves, which you use to cook things. And even deeper bass, longer wavelength, are radio waves. What is a bit surprising is that the light we humans actually see, the spectrum or rainbow of visible colors between the slightly higher pitched violet and the slightly lower pitched red, is a tiny band in the middle of a huge spectrum ranging from gamma rays at the high-pitched end to radio waves at the low-pitched end. Almost the whole of the spectrum is invisible to our eyes. The sun and the stars are pumping out electromagnetic rays at a full range of frequencies or pitches, all the way from radio waves at the base end to cosmic rays at the treble end. Although we can't see outside the tiny band of visible light, from red to violet, we have instruments that can detect these invisible rays. The picture of the supernova in Chapter 6 was taken using X-rays from the supernova. The colors in the picture are false colors, like the false white used to show the pattern on the evening primrose flower. In the supernova picture, false colors are used to designate different wavelengths of X-rays. Scientists called radio astronomers take photographs of stars using radio waves rather than light waves or X-rays. The instrument they use is called a radio telescope. Other scientists take photographs of the sky at the end of the spectrum in the X-ray band. We learn different things about the stars and about the universe by using different parts of the spectrum. The fact that our eyes can see through only a tiny slit in the middle of the vast spectrum, that we can see only a slender band in the huge range of rays that scientific instruments can see, is a lovely illustration of the power of science to excite our imagination, a lovely example of the magic of the real. In the next chapter, we shall learn something even more wonderful about the rainbow. Splitting the light from a distant star into a spectrum can tell us not only what the star is made of, but also how old it is. And it is evidence of this kind, rainbow evidence, that enables us to work out how old the universe is. When did it all begin? That may sound unlikely, but all will be revealed in the next chapter. Illusion, and understanding it leads on to all sorts of interesting things, some of which we'll come to in the next chapter. What light is made of. First, we need to understand about something called the spectrum. It was discovered in the time of King Charles II, that's about 350 years ago, by Isaac Newton, who may well have been the greatest scientist ever. He discovered lots of other things besides the spectrum, as we saw in the chapter on night and day. Newton discovered that white idea. The rainbow is seen as a definite thing in a definite place, a definite distance away. Well, you probably have worked out that it really isn't like that. First, if you try to approach the rainbow, no matter how fast you run, you'll never get there. The rainbow will run away from you until it fades away altogether. You can't catch it, but it isn't really running away because it isn't really in a particular place at all, ever. It's an illusion, but a fascinating. The real magic of the rainbow. When I was about 10, I was taken to London to see a children's play called Where the Rainbow Ends. You almost certainly won't have seen it because it is too unfashionably patriotic for modern theaters to perform. It is all about how exceptionally special it is to be English, and at the climax of the adventure, the children are rescued by St. George, the patron saint of England, not Britain, for Scotland, Wales, and Ireland have their own patron saints. But what I most vividly remember is not St. George, but the rainbow itself. How wonderful it must be to stand right in the foot of a giant rainbow. You can see where the author of the play got the idea. A rainbow really does look like a proper object, hanging out there, perhaps a few miles away. It seems to have its left foot planted, say, in a wheat field, and its right foot, if you are lucky enough to see a complete rainbow, on a hilltop. You feel you ought to be able to go straight to it and stand right where the rainbow steps on the ground, like the children in the play. All the myths I have described to you have the same. The children actually went to the place where the rainbow planted its foot, and we saw them walking about in the middle of the rainbow where it hit the ground. It was cleverly staged, with colored spotlights beaming down through swirling mist, and the children stumbled about in a spellbound daze. I think it was at about this moment that the shining armored, silver-helmeted St. George appeared, and we children gasped at the scene as the children on the stage shouted, "St. George! St. George! St. George!" But it was the rainbow itself that seized my imagination. Never mind St. George.